I'll do is I'll explain again how this works. With what we're doing with a man living in flatland, right? And in flatland there's a light on a pole, okay? And the guy here has a device that will measure the angle to the base of the light and then to there, right? Which we'll call H for height. Right, you can measure that. Right. Now, if he moves somewhere else, let's move him over to here. This is H2, that might be H1. That it'll be a different angle. But as you get closer, the angle gets bigger. As you go further away, the angle gets less.
Okay.
Right?
Yep.
And also, if you measure the same angle somewhere else, same H1, you must be on a circle around the base of the lamp, right? Okay. The same distance from the lamp base gives you the same angle. And that's basically the whole basis of celestial navigation. Now, of course, we're talking about a sphere instead of flatland and all that, but still, it's the same analogy. And this is called an LOP, line of position. And that's what you get from a sight. In general, you get one line that you're on. So to get a fix, you need two sights.
Right.
Or in the case of stars, you do three sights, and where the lines cross is where you are. Now what you do with the sun, as it conveniently moves across the horizon during the day, you take the sight 2 or 3 hours apart, and then you'll get a different sight, and you can move the first sight by the amount you've sailed, which is something you know fairly accurately. And where that crosses the second sight, that's called a running fix, and that's what you get. Right?
Okay.
And that's the way I sailed for years and years, by just doing running fixes twice a day. One fix in the morning, one fix in the afternoon, and that's where you were. Basically, another thing to bear in mind is that if you now look at a plan view of flatland, which is divided up into lines of latitude and longitude, and supposing the base of the lamp is here and you're here, then the angle from north is called the azimuth. It's the direction to the base of the lamp, right? So in this case his azimuth is 180, because you measure from north. Is the way I drew it. Let's say this was the sun and this was you. Then measure to north, that's 180. And that tells you something. As I say, the line of position goes through where you are, right? And so because it's a tangent to a circle, when the sun is directly south of you, the line of position is parallel to lines of latitude, which is why you get a latitude out of a noon sight. That you don't need to calculate where you are on that latitude, but you know your latitude. And people went around the world for centuries just navigating by latitude.
Yeah.
That's because conveniently the Atlantic and the Pacific lie north-south basically, and you can get the latitude of, like if you want to go to Cape Town, you get the latitude of Cape Town and you just sail east till you get there.
Right.
So that's the basic principle of how it works. Now in fact, when it comes to the use of a sun rather than a flat land, if this is the Earth, that's its North Pole there, and this is the equator. The lines of longitude all converge at the poles, right?
Right.
And the lines of latitude are parallel to the equator. And the base of the lamp is actually the point where the centre of the Earth connects to the centre of the Sun.
Okay.
So where it intersects the Earth on the surface, that's called the geographic position. And that's what all the calculations are based on, to convert all these angles into an actual line of position. And so as the Sun moves up and down, as the Earth tilts, and well, as the Sun, the Earth is tilted with respect to its plane. So as it goes around the Sun, the GP moves up and down by 23 degrees over the year.
Okay.
And that's called the declination. And it's listed for every day of the year. And in the old days, most mariners knew pretty closely every day what the declination was. Because you need to know that to do the calculation. So the other thing is that when you take a site, you bring the Sun down so it looks on that's the horizon. But you see, we're measuring a line from the centre of the Sun. Now the Sun is 30 minutes in diameter. So in fact you have to allow for the fact when you take a site, you really need to know something that's 15 minutes higher, right? And so there are corrections. What you get from the site is HS, and then plus errors equals what's called HO, which is what's actually used in the calculation. Now the errors are basically three things. One is errors. Semi-diameter. That's this. That you've got 15 minutes of error there. 15 minutes. And then there's height of eye. Now you're looking at the horizon from that height. So you're looking down at the horizon. So that changes the angle. Right? And that's called dip. And the almanac always has a correction for dip. But typically it's on a boat like this, it's 3 minutes. And then finally there's refraction. That as a ray from the Sun comes through the Earth, the atmosphere bends it. And so all of these things generally add up to plus 12 minutes. And this is called the fisherman's error. Now in the Navy, you look up each one separately and apply it to fractions of a minute, you know, for decimal. But yachtsmen and fishermen, they just add 12 to HS. So HO equals HS plus 12 minutes.
Okay.
Right? So all those sites we took now, we'd get an average for the noon. Now, as I say, because we're on the Greenwich time thing, it would be roughly noon when we get the maximum height. But in fact, we are 10 degrees, I mean, this way. So, are we 10? Yeah, I think we are, roughly. So, yeah, we're 10. Now each degree takes 4 minutes for the suns to move around. So it'll be 12:40 when it gets to us. Plus, there's another factor. The Earth does not go around the Sun in a full circle. It's called an ellipse. It's an egg-shaped circle. So it speeds up and slows down. And that means that noon is going to be, or I should say, zenith. Meridian passage is going to be slightly earlier, slightly later. And the almanac tells you that. Let me get an almanac here. And for reasons which escape me entirely, this gaining or losing on the meridian passage is called the equation of time. So for today, the equation of time is 4 minutes 44 seconds. So in fact it will be 4 minutes late because it's slowed down, and also we need to know the declination. And so if we look up August 14th for the sun, the declination is north 1422. In other words, it's 1422 degrees north of the equator. I'll put that here. Right, so we now have everything we need to know to do a noon sight.
Okay.
We know that it's going to be about 44 minutes late.
Okay.
And what we can do is have lunch, then go out about 12:35, 12:40, and start taking sights, and we'll plot. And we should see if we plotted it this way. This is the height. We should see a series of dots that do that.
Okay.
And then we find this one.
Right.
And then we do the arithmetic to get the latitude.
Great.